The performance of a fire sprinkler system depends on discharging the right amount of water onto the fire, and that discharge is driven by the available pressure. In this video, we'll break down key concepts in hydraulic calculations, including flow, pressure, and pressure changes, both losses and gains. These fundamentals are essential for designing systems that respond effectively when a fire occurs. Flow rate in fire sprinkler systems refers to the amount of water discharged over time, typically measured in gallons per minute or liters per minute. It indicates how much water the system can deliver to control or suppress a fire. Flow rate is represented by the letter Q. One way to calculate it is by multiplying the velocity of water in the pipe by the cross-sectional area. In other words, Q equals velocity times area. For example, let's calculate the flow rate of water moving at 8 feet per second through a pipe with an internal diameter of 1 inch. First, we convert the diameter to feet by dividing 1 by 12, which gives us approximately 0.083 feet. Then we calculate the cross-sectional area using the formula for the area of a circle. Area equals pi times the diameter squared, divided by 4. Once we have the area in square feet, we multiply it by the velocity to find the flow rate Q. The calculated flow rate is expressed in cubic feet per second. However, in fire sprinkler system design, we typically use gallons per minute. To convert cubic feet per second to gallons per minute, we divide by 0.002228. In fluid mechanics, pressure refers to the force applied per unit area within a fluid, often caused by compression. When water is compressed, its energy increases, and this results in higher pressure within the system. In fire protection systems, pressure is typically measured in pounds per square inch, or PSI, in imperial units. In metric systems, it's commonly measured in bar. When none of the sprinklers are activated, there is no flow in the system. The pressure shown on the gauges at this stage is called static pressure. Static pressure is independent of the piping layout between the water supply and the gauge. It depends solely on the elevation difference between them. For example, if the pressure gauges installed at the fire hydrant outlets and on the riser are positioned at the same elevation, they will all show the same static pressure. This is because static pressure depends only on the elevation difference between the water source and the gauge, not on the length or layout of the piping. In the diagram, we can see that the pressure gauge installed on the branch line is located closer in elevation to the water source compared to the other 3 gauges. Since static pressure depends on the elevation difference between the water source and the gauge, a smaller elevation difference results in lower pressure. Therefore, we can conclude that the gauge on the branch line will show a lower pressure reading than the others. Calculating pressure due to elevation changes is relatively simple. In imperial units, we multiply the elevation difference in feet by 0.433 to get the pressure in PSI. In metric units, we multiply the elevation difference in meters by 0.098 to get the pressure in bar. Let's say the elevation difference between the water supply and the outlet of a fire hydrant is 100 feet. To calculate the pressure caused by this elevation, we multiply 100 by 0.433. That gives us 43.3 psi of pressure due to elevation change. When a sprinkler activates, water begins to move through the piping network. In this flowing condition, pressure is affected not only by elevation changes, but also by other factors related to how water behaves inside the system. As water travels through the pipes, some pressure is lost due to friction between the water and the internal surface roughness of the pipe. Additional pressure loss occurs when the water passes through fittings, valves, or changes direction, introducing local disturbances and energy dissipation beyond the normal friction loss. The pressure that remains after these losses is called residual pressure, and it's what the gauges display during flow conditions. Now let's break down the three types of pressure that exist in moving water inside sprinkler piping. First, we have what's called velocity pressure. This type of pressure acts in the same direction the water is flowing. It's directly tied to the kinetic energy of the moving water. The faster the flow, the greater the velocity pressure. Next is normal pressure. This acts perpendicular to the pipe walls. It pushes outward, sideways against the pipe, not along the flow direction. And finally, we have total pressure. This is the combination of both, the vector sum of velocity pressure and normal pressure. When you add the forward push and the sideways push together, you get the total pressure carried by the water. In hydraulic calculations for fire sprinkler systems, we simplify things by assuming that velocity pressure is zero. In these systems, velocity pressure is relatively small compared to normal pressure, and ignoring it makes calculations easier and slightly more conservative. Velocity pressure still plays an important role in advanced hydraulic design and system optimization, and we'll explore that fascinating topic in another video. As mentioned in the previous section, when water flows through a pipe, it loses pressure due to friction. NFPA 13 outlines two formulas for calculating this friction loss. One of them is the Darcy-Weisbach equation, a more precise method that accounts for fluid properties and flow conditions through the use of a friction factor. While it offers greater accuracy, it's also more complex to apply. NFPA 13 specifically mandates the use of the Darcy-Weisbach method for antifreeze systems exceeding 40 gallons in volume. We'll take a closer look at this formula and how it works in another video. The other formula is the Hazen-Williams equation. This method is simpler than Darcy-Weisbach and uses just three key parameters to calculate pressure loss per foot of pipe: the flow rate, the C factor, and the internal diameter of the pipe. Despite its simplicity, the Hazen-Williams method provides an acceptable level of accuracy for most fire sprinkler system designs. That's why it's widely used in hydraulic calculations, especially when antifreeze systems aren't involved. In the Hazen-Williams formula, Q represents the flow rate, the amount of water passing through the section of pipe where we're calculating friction loss. Since Q appears in the numerator of the equation, we can see that as the flow rate increases, the pressure loss also increases. In other words, higher flow means more friction, and more friction means greater pressure drop along the pipe. The C factor, which represents the internal roughness of a pipe, is listed in Table 282481 of NFPA 13. This value depends on the pipe material, and for black steel and galvanized pipes it also varies based on the type of system. A higher C factor means a smoother pipe surface, which results in less friction loss. We can see this relationship clearly in the Hazen-Williams formula, where the C factor appears in the denominator. The larger the C factor, the smaller the calculated pressure loss, making it a key parameter in hydraulic design. The third parameter in the Hazen-Williams formula is D, which stands for the internal diameter of the pipe. In Annex A of NFPA 13, you'll find a detailed listing of internal diameters for various pipes and tubes. What's especially important here is the exponent applied to D in the formula, 4.87. This high power means that diameter has the greatest influence on pressure loss compared to the other parameters. Even a small change in pipe diameter can lead to a significant change in friction loss, making it a critical factor in hydraulic design. It's important to note that while increasing pipe size can reduce pressure loss, it doesn't always improve system performance. In certain scenarios, upsizing the pipe may actually lead to higher required flow rates and pressures for the sprinkler system, which can complicate the design rather than help it. We explored this interesting topic in more detail in an article available at nsvsoft.net. Now that we're familiar with the Hazen-Williams formula, let's walk through a practical example. As shown in this figure, two pressure gauges are installed on a 2-inch black steel Schedule 40 pipe in a wet pipe sprinkler system. Let's assume the distance between these two gauges is 30 feet, and the first gauge shows a residual pressure of 25 psi. With a flow rate of 200 gallons per minute, what pressure would we expect to see at the second gauge? In this example, the flow rate is 200 gallons per minute. According to Table 28.2481 of NFPA 13, the C factor for black steel pipe in a wet system is 120, and based on Table A 16.32, the internal diameter of a 2-inch black steel Schedule 40 pipe is 2.067 inches. With these values, we're ready to apply the Hazen-Williams formula and calculate the friction loss per foot of pipe, which comes out to 0.338 psi. Since the distance between the two gauges is 30 feet, and we've calculated that the water experiences a pressure loss of 0.338 psi per foot, it's easy to find the total pressure loss by multiplying the pipe length by the pressure loss per foot. By subtracting this loss from the first gauge reading of 25 psi, we find that the second gauge shows a pressure of 14.84 psi. This illustrates how friction loss affects pressure readings along the pipe and how the Hazen-Williams formula helps us quantify it. As mentioned earlier, when water flows through valves and fittings, additional pressure loss occurs. These components introduce local disturbances and cause energy dissipation beyond the normal friction loss in straight pipes. Although referred to as minor losses, they can represent a significant portion of the total energy loss in a system. In fluid mechanics, we calculate this pressure loss using the formula H equals K times V squared divided by 2G. In this formula, H is the head loss, K is the loss coefficient for the fitting or valve, V is the flow velocity, and G is the acceleration due to gravity. The value of K depends on the type of valve or fitting and must be carefully selected from valid references such as engineering handbooks or standards. NFPA 13 introduces an easier method for estimating pressure loss through valves and fittings, known as the equivalent length method. In this approach, each common component is assigned an equivalent length of pipe based on its size and type. These values are outlined in Table 28.2311, allowing designers to calculate pressure loss by treating fittings as additional pipe length. For example, the equivalent length of a 4-inch vane-type flow switch is listed as 30 feet. This means that the pressure loss the water experiences while passing through this device is equivalent to the pressure loss from flowing through 30 feet of 4-inch Schedule 40 pipe with a C factor of 120. It's important to note that the values in Table 28.2311 are based on Schedule 40 pipe with a C factor of 120. Therefore, in sprinkler systems where the pipes are not Schedule 40 or the C factor differs from 120, appropriate correction factors must be applied to ensure accurate pressure loss calculations. Finding the correction factor for a C factor different from 120 is quite straightforward. NFPA 13 provides these values in Table 28.2321. All we need to do is select the correction factor based on the pipe's C value and then multiply it by the value obtained from the equivalent length table. For example, if a 4-inch vane-type flow switch listed in the table with an equivalent length of 30 feet is installed on a pipe with a C factor of 150, we simply multiply 30 by the correction factor of 1.51, which gives us an adjusted equivalent length of 45.3 feet. It's interesting to note that the correction factors for different C values may seem counterintuitive at first. We might expect that higher C values, which indicate smoother pipes, would have smaller correction factors than lower C values, which represent rougher surfaces. But it actually makes sense, because the equivalent length of a fitting or valve reflects the pressure loss it causes. When the C factor is lower, the pipe is rougher and therefore creates more friction loss. In other words, rougher pipes create more friction, so the same amount of pressure loss occurs over a shorter length. When adjusting for smoother pipes, we need to extend that length to match the same pressure loss, which is why the correction factor becomes larger. Now let's review the correction factor used when the pipe is not Schedule 40. In these cases, NFPA 13 provides a formula to calculate the adjustment. First, we find the internal diameter of the actual pipe. Then we divide it by the internal diameter of Schedule 40 pipe of the same nominal size. Finally, we raise the result to the power of 4.87 to determine the correction factor. For example, if a 2-inch 90-degree standard elbow is installed on a Schedule 10 pipe, we need to calculate the correction factor. First, we find the internal diameter of the 2-inch Schedule 10 pipe, and then internal diameter of a 2-inch Schedule 40 pipe using the reference table. Next, we divide the Schedule 10 diameter by the Schedule 40 diameter and raise the result to the power of 4.87. This gives us a correction factor of 1.23. By multiplying this factor by 5 feet, the equivalent length of a 90-degree standard elbow, we get a final adjusted equivalent length of 6.15 feet. In some cases, we may need to apply 2 correction factors, one for a different internal diameter and another for a different C factor. When this happens, simply multiply both correction factors by the value obtained from the equivalent length table to get the final adjusted length. Finally, if a valve or fitting is not listed in the equivalent length table, we should refer to the product's data sheet for pressure loss information. In most cases, these values are based on Schedule 40 pipe with a C factor of 120. So, if your system uses a different pipe type or C factor, make sure to apply the appropriate correction factors to ensure accurate calculations.